Hello everybody. Last time we said that there are two fundamental principles in a special theory of relativity. The first one is that the laws of physics are the same in all the inertial reference frames. The second fundamental assumption is that the speed of light is the same in all the inertial reference frames. Starting with these two postulates, Einstein made the huge revolution concerning the space and time. Let's talk about time as our first objective. To do that, to talk about time, we need to introduce a clock. What is a clock? A clock is just a device that we use to measure time. We could use a mechanical watch. We could use a pendulum. We could use, Galileo did, our heart beat, and so on. But we want to use a simple and efficient clock. And let me sketch this simple clock on the blackboard. I call it a light watch. What is a light watch? A light watch is just a simple long pipe, a vertical pipe like that, if you want, with a circular section or a square section, doesn't matter. It is an empty pipe, closed at the two ends, and here we have two mirrors. This is a mirror, and this is another mirror. So the two end surfaces are made with reflecting material. In this way, we can imagine that a photon is going up and down, bouncing at one mirror, going to the other mirror, and so on, continuously. Okay, and suppose for simplicity, that the height of this pipe is just equal to 300,000 kilometers. So a very, very long pipe, more or less the distance from here to the moon. Okay, so we say that this is long 300,000 kilometers. But if it is 300,000 kilometers, the time, okay, for a photon to bounce from one mirror to the other is exactly 1 second. So this is our photon going up and down, and from here to here, okay, the time lapse is just 1 second. So as we know that we know from the simple formula that the space traveled by a body moving is just equal to the velocity times the time necessary to run on this distance s. In the case of the photon, we have just like that. So the space that a beam of light run in one time, in a certain interval of time t, is exactly c times t. So in this case, the height of this pipe is exactly c multiplied by 1 second. So we can assume that the length of the pipe is exactly c. Now we have this situation here. Here I have my friend Mr. A standing still on the Earth, and imagine that the clock that we have defined before is exactly over his head, standing still as well. So every 1 second the photon is bouncing up and down. Now, suppose now that I have another identical watch like this that is moving in this direction with a speed equal v. After 1 second, I suppose that at t equals 0, the two watches are one behind the other. Okay, so they are exactly in the same position, considering this x direction. They are, both of them are above the Mr. A head. But after 1 second, if this watch that is eventually coming from this direction, moving with velocity v, and at t equals 0 is exactly over the A head. After 1 second, the second watch will be here, because the space that the second watch has run will be v times t, but t is equal 1, so it is equal v. Okay? Well, now, suppose that at the time t equals 0, both the photons bouncing up and down in this clock, the still one, and in the other clock, were exactly in the position of the low mirror. Okay. After 1 second, we know that the photon of the still watch will be exactly touching the upper mirror. What about the photon in the moving clock? Well, as we know that the speed of light must be the same in all the inertial reference frames, and you can consider the still clock and the moving clock as two inertial reference frames, because this is still and this is moving with constant rectilinear velocity. The speed of light must be the same. So what this means? This means that if I have Mr. B on board of the moving clock, what happened to this the photon inside the moving clock? Well, you have to consider that for the observer A, you will see the photon moving in this way here. Because this is a circle indicating that, oh, very bad circle. Anyway, a circle indicating that the speed of light must be c and not more than c. Let's do it better. Oh, this is not much better. This is the radius, like that. Okay. So what's happening? The situation is that in the meantime that the photon as seen by observer A has arrived here, okay, the photon in the still watch will be up here. So you see that what A observes is that the photon in the moving watch has not yet arrived at the top. That means that he sees the physical events happening in the moving reference frame going slower than the event in the still reference frame. In particular, we can simply calculate this difference using, in a very trivial way, the Pythagoras theorem, because we know that this is C and this is C as well, because it's the radius of a circle. This is V, so this vertical path of the photon in the moving watch, let's call it X. No, X is this. Let's call it H. H squared is equal C squared minus V squared. Okay? But now we can simply state that from here that H is equal to the square root of C squared minus V squared. Another step, let me write like this, the formula. What have I done? I've done simply a factorization. I have factorized a term c squared. If I distribute back, you see that I've got c squared times 1 is c squared minus c squared times v squared over c squared is again v squared. So nothing difficult. Then this is the product of two factors under the square root. I can bring the c squared under out of the square root. Okay, so I see that the ratio from here, I see that, that h is equal c times the square root of 1 minus v squared over c squared. Well, but you certainly agree that if I write the ratio between h and c, that is obtained dividing both members by c, this ratio here corresponds to the ratio between the two intervals of time measured in the two reference frames. In particular, Mr. B can obviously say that his time is going slower than the time of Mr. A because the photon has not yet reached the upper side of the pipe. And so we can say that let's call now the time, the interval of time corresponding to Mr. B, let's call it delta tau. You know that the symbol delta means difference, an interval. And so when I say delta tau, I mean the interval of time. But for the moment, we can simply call it tau. That is the time measured by Mr. B. And let's simply call t the time measured by Mr. A. So the ratio of the two times will be simply like that. And at the end of the day, we can write the final formula, that is that tau is equal t times 1 minus v squared over c squared. Okay, this is the famous formula for the time dilation in special relativity that demonstrate that if you assume as true our two fundamental postulates. First, I'm sorry, I continue to repeat them and I'm becoming boring, but they are so important that we must recall them every time. So first of all, the first one is that The laws of physics are the same in all the inertial reference frames, moving in a straight line with a constant velocity, one relative to the other. And second fundamental postulate is that the speed of light has exactly the same value in all the inertial reference frames. With using just only these two postulates, we have proved that the time is not a unique universal time equal for everybody. But we have seen that in particular in this simple case, the time measured by the moving man B traveling at speed equal v, the time tau, is equal to the time t for the standing still man A multiplied by the square root of the factor 1 minus v square over c square. This is the first fundamental formula in special relativity. We will use it many times. And for the time being, I want to add the final consideration that this time that we have indicated with the letter tau is what is called the proper time. We call it proper time, indicating that is the time of the man that is on board on the moving frame. Okay, this is a very important result, and we will use it so many times in what is following. Well, I want to conclude this this second talk with a simple exercise, just to use the formula we have found. Okay, let's suppose that a spaceship is traveling at a constant speed from the Earth to Alpha Centauri. And this is the Earth. This is Alpha Centauri. And the spaceship is traveling with a constant speed, suppose that is equal to, this is the starship, suppose that the speed is 1/2 of the speed of light, c over 2, okay? And we know that the distance from the Earth to Alpha Centauri, as measured by Earth, okay? This is Mr. A standing on the Earth, and here we have Mr. B on board of the spaceship. So Mr. A knows that the distance between the Earth and Alpha Centauri is 4.5 light years. Okay? C/2 is the speed. Okay? Well, the question is, how long will be the trip for the two men, Mr. A and Mr. B? Okay, we know that the time, the terrestrial time, let's call it T, is equal to terrestrial time, while tau is equal the spaceship. Time. Okay. Well, we know that the time for the let's calculate the time for a return trip. Okay, so Mr. B leaves the Earth and reaches Alpha Centauri and comes back. We have to imagine that the velocity is not changing, so it is quite unrealistic. No, okay, so it's better for the moment. Let's consider just only the spaceship traveling continuously in a straight line. So there is a moment of time, an instant of time when they are in the same position, is passing through the Earth and then continuing towards Alpha Centauri. So we know that the time that is Mr. A calculate and says effectively for the spaceship to reach Alpha Centauri will be the double of 4.9, because the formula is simply, we know that the distance, let's call L is the distance, is 4.5 years, okay? And we know that the time T for Mr. A is just simply the distance divided by the velocity. So it is L divided C over 2. That is equal to L over C. That is equal to 2 times 4.5 light years divided divided 1, sorry, light years, I have to do like that, 4.5 light years multiplied by 300,000 kilometers per second divided 300 times. Doesn't matter, it's simply like that. Okay? Yes. Okay. It's quite obvious. If the distance is 4.5 light years and the spaceship is traveling half the speed of light, the light needs 4.5 years to reach Alpha Centauri, the spaceship doubled, that is 9 years. Okay. What about the time measured by Mr. B on board? Tau is equal T times this formula here. So we know that T is 9 years times what? The square root of 1 minus V square over C square. But V square is C square over 2 square, which is 4, divided C square. So it is 9 years times the square root of 1 minus 1/4, that is 3 over 4. And so this is equal to 9 times the square root of 3 over 2. That is more or less 7.8 years. So the result is quite interesting. We see that the time measured by Earth is for the starship to reach Alpha Centauri is 9 years. The time as measured by the starship itself is 7.8 years. This is due to the fact that the speed v of the spaceship is quite high. It is 50% of the speed of light. If you increase the speed of the spaceship, you see that the formula produces an astonishing result. That at the limit, if v is equal to c, you have 1 minus 1 is 0, and so the time as measured by the person on board, it is frozen. So no time passing from him, or if you prefer, he reaches Alpha Centauri immediately. The two events, starship passing through the Earth and reaching Alpha Centauri, are simultaneous in the case of V equals C. But we know that we will see that no massive bodies can reach the speed of light. They can arrive as near as they want using huge amounts of energy, so it's quite technically impossible at the moment, but in any case you cannot reach exactly the speed of light. So this number here can't be exactly 0. So the simultaneity of this event, leaving Earth and reaching Alpha Centauri, can't be obtained. Okay, but it is interesting if you can try to do calculation, assuming, for instance, a speed v equal 99% of the speed of light, and you see that probably you can reach Alpha Centauri just in few hours. That is quite good, because for an astronaut affording so long trip, it is interesting that the fact that he can reach probably these faraway stars in a relatively small time on board. On the other side, on the Earth, the time needed for the luminar spaceship traveling at almost the speed of light will be always more or less the equivalent to the distance of the star. If you imagine a rocket going towards the Andromeda galaxy, that is 1 million light years. Okay, if the rocket is traveling at a 99.99% of the speed of light, for the persons living, the humanity living on the Earth, they will see, if they are still alive, I mean, the next generation will see the starship reaching the Andromeda galaxy after 1 million years. And probably on board, I don't know, I have not done the calculation, but if you travel at 99.99% of the speed of light, you need just only maybe a few months, okay? And this is an interesting result coming out from this fantastic formula that definitely states that the time is not just a unique universal dimension, but is relative to this system that we are that we have in the game. Okay, so thank you for the moment, and see you soon.